You type a prompt into a chat window, getting back code or a summary in seconds. It is an experience of total digital seamlessness. But that interface is the surface layer of a massive physical industrial world. The ambition for machine intelligence is decades old. Researchers were laying the theoretical groundwork for neural networks, like backpropagation, a training algorithm that lets a system learn from its own errors, as early as 1986. For years, those ideas stalled. The math worked on paper, but the world lacked the computing power and the vast pools of digital data required to turn theory into a functional product. Modern AI resulted from two distinct histories aligning: a research track of algorithms and neural networks, and a hardware track of optics, fabrication, and global infrastructure. The 2020s AI explosion happened because these parallel tracks compounded out of sight before finally colliding. A defining moment in that collision arrived in 2012 with a system called AlexNet. By feeding millions of labeled images into a deep neural network, researchers decisively outperformed older, hand-coded pattern recognition methods. The secret to this software victory was a specific type of hardware, the GPU, or graphics processing unit. Originally built to render high-speed pixels for video games, GPUs are structurally designed to perform thousands of simple mathematical calculations at once. This parallel processing turned out to be the exact requirement for training large neural networks on massive datasets. The foundation of modern machine learning is built on repurposed gaming hardware. From this point on, AI's progress became tethered to the production limits of the global chip industry. In 2017, the research track underwent another major shift. Google researchers introduced a new neural network architecture called the transformer. Older models read text word by word, which limited their speed and context. The transformer replaced this with an attention mechanism, a mathematical process that looks at an entire sequence of data at once to map out the relationships between every piece of information. Because this architecture processed data in parallel, researchers could run training workloads across vast arrays of chips. The size of these models began to scale upward as fast as the industry could build the hardware. The software was now capable of ingesting the entire internet. To do it, the industry required computing power on a planetary scale. Meeting that demand required a hyper-specialized physical supply chain, a ladder of industrial dependencies that runs from microscopic optics to massive data centers. The origin point is optical engineering. Companies like Zeiss SMT design ultra-precise mirrors for lithography machines built by ASML. These systems use extreme ultraviolet light to print microscopic transistor patterns onto silicon. Manufacturing foundries like TSMC use those lithography tools to physically etch nanoscale patterns into wafers of silicon. Inside automated fabrication plants, these wafers are processed and assembled into advanced packages that stack memory and logic together to maximize data transfer speeds. Designers like NVIDIA take this silicon and engineer it into dedicated AI accelerators. They also provide the software layer, like CUDA, a platform that allows developers to program GPUs for general-purpose computing to make the hardware accessible. Finally, tens of thousands of these accelerators are networked together inside massive cloud supercomputers. An AI model is the physical output of the most complex industrial manufacturing organism ever assembled. By 2020, labs like OpenAI proved that increasing parameters, data, and compute reliably scaled up raw intelligence. To make that intelligence useful, researchers added alignment frameworks. These include RLHF, reinforcement learning from human feedback, where humans ranked answers to teach the model preference, and constitutional AI, a method where the model is given a written set of rules to evaluate its own behavior. On November 30th, 2022, ChatGPT translated this underlying power into a simple chat interface. Suddenly, the general public could use a technology that had been building for years. This was the intersection of the entire story. The research track and the hardware track finally reached a point of high visibility collision. In 2022, 40 years of theoretical research and 40 years of manufacturing progress finally reached the surface at the same time. Once that convergence happened, AI escaped the lab. Frontier models were hosted in the cloud and exposed through APIs, software bridges that allow different programs to talk to each other. integrating AI into search engines and office tools worldwide. Because AI is now global infrastructure, its future is dictated by physical bottlenecks. Progress is limited by memory bandwidth and the speed at which fiber optic cables can move data between thousands of chips. There is also the challenge of energy. Expanding the AI boom requires massive amounts of electricity and industrial cooling systems to keep the world's training clusters from overheating. Every time you type a prompt, you are activating a massive vertical stack. The interface relies on the model, which relies on the training pipeline, the server racks, the chip packaging, the foundries, and the extreme ultraviolet optics. Modern AI is a physical industry. Its future will be decided by the hard limits of atoms, energy, and supply chains.